with the first talk, so which will be given by Abhinav Valada.
All right, can you
share? Is it possible?
I think you need to stop sharing.
Okay. Okay.
Are you able to see my screen?
Yes, now yes.
Okay, perfect. All right. Hello, everyone. I'm Abhinav. I'm an assistant professor and head of the Robot Learning Lab here at the University of Freiburg in Germany. And today I'm going to talk to you about our work here that we've been doing on self-supervised learning for various perception and tracking tasks for different autonomous driving applications. So with that, let's get started. So as you all know, data-driven intelligent vehicle applications have tremendously grown over the last years, which are primarily fueled by the progress that we have made in machine learning and deep learning in particular. So in the beginning, what we've been focusing on a lot is how do we make these individual tasks, individual perception tasks or state estimation tasks, work really well with specific data. But what the problem that we're facing is that these individual models do not scale when it comes to deploying them on real-time applications such as autonomous driving or robotics. So this is primarily because we have to deploy many of these individual models that are very specifically tailored for each of these tasks. And another problem is that we have primarily focused on supervised learning, right? And this requires large amounts of annotated data. And this also leads to the problem that it does not scale when we think about having to label each specific application for each specific environment. And I really like this quote by Pierre. He basically coined this quote saying that give a robot a label and you feed it for a second, and teach a robot to label and you feed it for a lifetime. So what we've been doing so far a lot is give a robot a label and you feed it for a second. And when we go to a new application, then we got to do this whole process all over again. So this is primarily what motivates my talk today. So let's start with some of the most basic perception tasks. So I think we all know about semantic segmentation. Here, our goal is to assign semantic class labels for each pixel in the image. And the problem with this is that there's no reasoning about instances. So here we only want to label basically each pixel of the class, which category does it belong to. We have another complementary task here, which is instance segmentation. And in instance segmentation, we care more about identifying individual objects or instances of the same class, and we don't necessarily consider the background semantics itself. All right, so very recently, about 2-3 years ago, this new perception task called Panoptic segmentation, I'm sure most of you might have heard about it as well, which is a combination of semantic segmentation and instance segmentation. And this is one of the tasks that we've been focusing on a lot in the last couple of years. And I would briefly describe one of our architectures that we published earlier this year in IJCB. So at a high level architecture, I hope you can see my mouse. At a high level architecture basically consists of a backbone network, which is shown in pink. And here we build our backbone network based on the efficient net architecture with certain modifications. And on top of this backbone, we have our two-way FPN, or our two-way feature pyramid network. Now, our two-way FPN fuses features in a bidirectional manner from the encoder. We have a top branch here and then a bottom branch here. And then the green blocks that you see here basically aggregate these bidirectional features that have been fused from the encoder. We then have our task-specific heads, one for learning the semantics and the other in the bottom here, learning for instances. And we have our Panoptic fusion module, which combines these logits from both these heads, which give you then the final Panoptic segmentation output. All right, so we evaluated this on diverse data sets, mostly in urban outdoor driving scenarios. So we evaluated this on Cityscapes, the Indian driving data set, KITTI, and Mapillary Vistas. Really quickly, some qualitative results. We can see that these scenes are extremely diverse, not only in the ways in the appearances, but also in the number of actors in the scene, the density of the actors in the scene, and the camera resolutions, and so on. And our method was primarily ranked #1 on all of these 5 benchmarks for panoptic segmentation. Our efficient PS model is also ranked 2nd if we can individually also evaluate them for semantic and instance segmentation. And here we were ranked 2nd, even though we do a much difficult task for panoptic segmentation. On the bottom below, you can see the leaderboard standing at that time on 2 of our variants, one that is pre-trained on the Mapillary Vistas and the other which is directly trained on the Cityscapes dataset. And the interesting thing here to notice is that we not only wanted to achieve the state of the art, but we also wanted to do this in the most efficient way as possible. So our model is basically among the top, I think, 20 approaches on the leaderboard, the most efficient, while achieving also the highest performance. And it's also the fastest and in terms of the computation as well. So most recently, our method was, we also took part in the end of last year on the ECCV Robust Vision Challenge. So in this challenge, unlike evaluating models on specific data sets, we have to create a single model that works well on over 6 different data sets, which includes both indoor and outdoor environments. And in this we have more challenges because we have over 100 different semantic categories that we want to simultaneously identify. So let's quickly take a look at some qualitative results. I hope the video is playing. So here you can see that our network accurately identifies both the background as well as the instances. So the instances here are denoted with a white background around them, as you can see. We can also see that our network accurately classifies faraway objects as well as objects that are near pretty accurately. So we open source all the code for these models. So if you're interested, you can visit our lab's website or this address that you see here to train your own pre-trained models from these. All right, so most recently, we also looked at if we can also do the same with LiDAR scans. So LiDAR scans substantially give up more different challenges than camera images. So LiDAR point clouds are inherently unordered in nature, and this makes it difficult for directly employing convolutional neural networks. And the sparsity of the LiDAR data decreases with distance, hence farther away objects have very few points. And you might say that why don't we just directly employ 3D convolutions, but these 3D convolutions require substantial amount of memory and time, which makes them unsuitable for real-time applications such as autonomous driving or in robotics. And well, we can do another thing where we can project our LiDAR scans in 2D. And the problem that we face here is that we have certain projection-related information loss when we project this point cloud. So this doesn't give us as good as performance as we would do while learning directly in the 3D space. So we took a look at these challenges and we proposed our new architecture. This work is still under review. So here we built upon our efficient PS model that I just described before, and we adapted it basically to the LiDAR domain, and we propose certain key modules. So what we do here is that our input to our network is basically the range image, the intensity, and XYZ distances. So we first pass this to our proximity convolutional module. So here we proposed a new type of convolutions that are called proximity convolutions. I will describe them in the following slide. Again, we have our encoder, our two-way FPN for feature fusion. We then have REN, or a range encoder network. So the main goal of this range encoder network is to take the range image and adapt the convolutions based on the range image that you see here on the left. And then we again have our semantic head and our instance head. And we also replace the normal convolutions which are with our proximity convolutions and our address proximity convolutions in the semantic head. So once we have our predictions in the 2D space, basically, we then use a k nearest neighbor scheme to then project it back into the LiDAR, LiDAR domain, into the 3D domain again. Okay, so as I said, we introduced our new type of convolution that's called proximity convolutions. So as we know, standard convolutions are limited in their geometric transformation modeling capacity due to this very fixed grid structure. And they also have this distance-dependent sparsity in LiDARs that further make this problem more adverse. And to tackle these constraints, we basically proposed our proximity convolution module. And here our convolution exploits the range information to augment the sampling locations of the standard convolutions. And this basically improves the modeling capacity. So in the figure, we can show an example here. So if we just take these red patches that is annotated here and we zoom in. So if we apply a standard convolution on a 3x3 grid at this yellow dot, as we can see here, we would sample the locations something like this in an adjacent manner. But if we employ our proximity convolutions that takes the range of the of this sampling point, the yellow point that you see here, then we would sample locations for this 3x3 convolution where we have the same range in the range channel. So that's why we would get some kind of sampling location as you see like this. And this basically enables us to capture information for objects even when they have less number of points, as shown on the green box. And this gives us substantially better performance in comparison to standard convolutions. So we also employ this our module in different parts of the network. Here we employ it in our semantic head. So we here devised a version that's called range-guided depth-wise separable address convolutions. So if you're familiar with address convolutions, here we also use a range-guided version of it, where in standard address convolutions, we have these holes that we enter in between the sampling locations, something like we see here in the bottom. And this gives us a larger receptive field. Now, if we just employ the normal version, we will have a fixed grid structure, and this will employ the same grid structure in different depth locations. But here we augment it to adapt according to the range values. So this is why in the bottom figure that you see here, as we go to further distances, we have more denser sampling in the grid, in the convolutional grid. So this gives us, this makes us capture the features for faraway objects more accurately than employing standard convolutions. All right, so I'm not going to go into too much detail. So we also proposed a new loss function for accurately capturing the object boundaries in also taking the range information into account. Okay, so we evaluated this on two different data sets. On Semantic KITTI and on New Scenes data set. Semantic KITTI has much more denser LiDAR scans compared to New Scenes. Well, New Scenes is much more challenging because just of the diversity in scenes compared to Semantic KITTI, which are primarily residential areas. So we are still number one on the Semantic KITTI and new scenes data set for Panoptic segmentation. We also proposed a pseudo labeling framework where we can use our trained model to then bootstrap to model to get further labels from unlabeled scans. And we also get a substantial performance improvement if we employ this pseudo labeling framework. So pseudo labeling is one way to one way that we can leverage unlabeled scans or data to further improve the performance. And you can see the leaderboard standing here on Semantic KITTI and new scenes. So I'd like to advertise one aspect here. We're also organizing the new scenes challenge for semantic segmentation and panoptic segmentation at NeurIPS this year. So if you're interested, then please keep a lookout for the new scenes challenge. All right, so some qualitative results really quickly. Here we see results on the Semantic KITTI data set. We also release a pre-trained models and the code. So if you're interested, you can go to the link here and try it out yourself. So here we can see pretty accurate results. The road is basically annotated in this pink color. So one thing that you might notice is that the instances basically flicker, and this is because there is no temporal consistency with it in between the scans, right? So we only classify the scans as they come in, and this is basically brought us to the next following work that I'm going to describe about. So our normal panoptic segmentation basically doesn't take any temporal information into account. But if we think of this in all our real-time or real-world applications, we have this streaming data that comes in from our sensors, right? So we asked this question if we can leverage this temporal information into account to further improve the performance of our models. And this brought us to a complementary task once again called multi-object tracking, where we just use bounding box information to track objects across the frame. And here we ask the question if we can combine both of these, because in real world applications, basically we use both of these tasks in robotics or in autonomous driving. So can we learn both of these tasks together to solve these problems, exploiting the cues from both of these individual tasks? So this motivated us to coin a new task that is called panoptic tracking or multi-object panoptic tracking. Here, we define the task as, in addition to panoptic segmentation, we want the instances to have these temporally consistent instance IDs. So we want to track each pixel belonging to an instance, or each point if we consider this as LiDAR scans. So what is the use of this? So the main goal is to encourage holistic modeling of dynamic scenes. This can be thought of as a cognitively more inspired way of handling dynamic scenes. And this basically will unify semantic segmentation, instance segmentation, and object tracking. And to our surprise, we were actually the first to think of this as a joint task. And this not only enables us to give better performance, but also more efficient and scalable models for dynamic scene understanding. All right, so we once again build upon our efficient PS architecture that we saw in the beginning. So in addition to our instance head and our semantic head, we also added basically an instance tracking head. And we then combine these in our Panoptic Fusion module. So how does our instance tracking head work? So we basically leverage the multiple objects detected by the instance head, the ROI, aligned features, the predicted class, and the mask logits. And we now input this to our tracking head that you can see in green here. So we then employ what is called as mask pooling, in which we eliminate the background pixels inside the bounding box. So we only take the features that belong to inside the instance mask regions. And we then use this to learn an embedding space where the feature vectors of the same semantic class and the track ID are mapped close to each other in the metric space, while segments of different instances are mapped far away from each other. So this is a form of metric learning that we employ here. So we then have our own similar Panoptic fusion module, which combines the features from all of these to give our output here, which is instances that are consistent across time as well as the background. So we evaluated this on 2 data sets, Virtual KITTI 2 as well as Semantic KITTI. So these 2 data sets support this task basically. And to our best knowledge, there is no existing method at that point. There was 2 methods that came after this work. It's called video panoptic segmentation as well as STREP. So at this time, there was no existing method that was tackling this task. So basically, to evaluate this, what we did is we took state-of-the-art panoptic segmentation and state-of-the-art multi-object tracking or multi-object tracking and segmentation networks and combined these. So that's what we see as baselines here. And an interesting fact is that we not only achieve better performance than state-of-the-art individual task-specific networks, but we're also more efficient in parameters and comparable inference time. So this is a good way to show that we can get more scalable models as well as achieve better performance if we exploit multitask learning, which is what we do here. We also did the same thing for LiDAR-based multi-object tracking and segmentation on the Semantic KITTI, and we see similar results where we achieve not only better performance, but we're also more efficient than individual task-specific models. Very quickly, some qualitative results. We can see for the most part, the instances have the color temporally. This shows that the instances are being tracked. Still not perfect. Sometimes when we have occlusions, the tracking basically fails. But for the first attempt, I think this is pretty decent results. We also see the same here in the video for LiDAR scans. On the left, we see basically normal panoptic segmentation. This is why the instances, when we consider the temporal dimensions, the colors get mixed. Well, if we track these instances across different scans, we see that on the right here that we get instances with temporally consistent colors or instance IDs here. This shows you that the instances are being tracked accurately. All right. So the next question that we asked here is that so far the methods that we have looked at still leverage annotations, right? So an important aspect here that we asked ourselves is, can we exploit self-supervision for semantic scene understanding? And here we basically wanted to address the task, not the entire scene, but only terrains. So one of the ways that we came up with to tackle this challenge is that robots often have multiple sensors, right? And multiple modalities. So here we wanted to see if we can leverage complementary modalities on the robot to self-supervise a different modality. So what does this mean? So first, for the task itself, so our goal here is to classify different terrains. So we want to be able to classify if the terrain is asphalt, if it's a grass, or if it's cobblestones and so on. And most robots need to do this. Many autonomous cars also do this. And here we basically have an idea that we equip our robot with a microphone, and we want to train an audio classifier that only uses the audio signals to learn in an unsupervised manner. So once we have this audio classifier, we then want this audio classifier to train a visual classifier in a self-supervised manner what the terrains are. So you can think of this as, by hearing what kind of terrains you want it to teach the camera what it sees. We can do this by exploiting SLAM, because if we imagine that the robot is traversing a type of terrain and that's being classified by the audio, at some point of time when the robot is at the visual location with odometry or SLAM, we can then associate what terrains are below the robot to what it will see in the future. So we exploit this in the form of self-supervision. So how does this work? At a very high level, what we first do is that we project the camera images into a bird's eye view representation, as you see here. Then we can only classify the terrains that are below the robot from the audio classifier, right? So then what we do is we have these classification locations in the bird's eye view, and we employ our unsupervised audio clustering approach to give labels to these visual terrain patches that you can see here. So we have these sparsely labeled images that we then employ a pre-trained semantic segmentation network for terrain classification. So how does this happen in a little bit more detail? So this is what our semantic labels look like. So because we only can classify terrains where the robot has gone before. So these are basically what you see here are the paths that the robot has traversed into different semantic categories. So how does this self-supervision happen? So what we do is that we do some kind of metric learning here. So we again take a positive pair, we sample positive pairs and negative pairs, and positive pairs are samples that are close to each other, and negative pairs are samples in the audio that are far away to each other. We then do unsupervised audio clustering. We also do reconstruction here to improve the performance. So what we do now after the unsupervised clustering has been trained is that we know samples that are close to each other in the audio space. So we also take similar samples that are close to each other in the visual space. So meaning if two samples are close to each other in the audio space, we take corresponding samples that are for the same terrain patch as close to each other in the visual space. So this gives us automatic clustering according to how the audio happens similarly in the visual domain. And this is what that we exploit for self-supervision. So we can compare this with fully supervised classification. If you had labels, that's the right column here. And if we compare this, we see that we achieve near comparable performance to fully supervised clustering. And I think this is really impressive that without any labels, we can get very comparable performance to fully supervised learning for terrain classification, as you can see here. All right, so some qualitative results really quickly, just before we run out of time. We can see we still have some false positives here. This is because we have grass in between these stones, and this is why you get these patches that are not really coherent here. All right, so what can we use this for? One of the things that we can use this for is for terrain adaptive planning. In robots, we use this a lot in mobile robots for adapting the paths based on the terrains. And that's what you see here. We build a semantic terrain map as the robot is traversing the environment, and we adapt our path planning instead of the shortest path that you can see here in blue. We take a more adaptive path that's more energy efficient as well as safe that we can see here. All right. So last work I'm going to talk about, I think it's the most coolest work that we have done so far. Here we ask the question, can we exploit the co-occurrence of modalities for self-supervision? So what does co-occurrence mean? Co-occurrence is that when we record sensor data simultaneously with multiple sensors at the same time, can we exploit this fact that these modalities exist at the same time for self-supervising another modality? So the task that we basically want to address here is multi-object tracking. So what we do here is we show three different modalities here in the visual space. I don't know, I'm afraid you can't hear the sound here, but there is background noise that's going on. So we exploit 3 different modalities, that is RGB images, depth, as well as thermal data. And we use these visual modalities to teach the audio how to track. And while deploying, we only want to hear the noises in the environment, or we want to hear the sounds of the vehicles and inform our autonomous vehicle here where the object is in the camera frame. So how can we do this? So the way that we, first, we of course have to collect a data set. You can see our car here in Freiburg. We basically equipped a car here with audio ring with 8 different microphones in different directions. And we have our camera here. We also have our LiDAR that you can see here on the top, and the thermal camera. So if you're interested in this data set, we have over 300 kilometers of driving data from multiple different sensors. You can access this at the website, as you can see here. So how does this work? So what we do is we use a teacher-student paradigm. So for the first time, we introduced a multi-teacher training approach in which we take pre-trained audio detectors, pre-trained visual detectors. That's what you see here. So each of these pre-trained modality-specific detectors are shown here in green, in blue, and in purple here. So these are just any pre-trained detectors. So then these are our teachers, and then we have a student network here, which takes audio. So while training, what we do is that we try to minimize the loss such that the features of the teachers and the students are as close to each other. So for this, we proposed our multi-teacher alignment loss, and then we also employ the focal loss. That's a pretty standard detection loss that you can use. And then while deploying, we basically throw away the teachers. That's the left part that you see here, and we only use our audio network. So what the output is of this network is that the input is the spectrograms and the output is the bounding box coordinates in the visual frame without any visual input. So I'm going to quickly skim past through the slides here. We proposed multi-teacher alignment loss, which basically computes the KL divergence between the teachers and the students to bring them as close as to each other as possible. And we also proposed a self-supervised pretext task. Here it's for car counting, and this further improves the audio student learning. So some quantitative results, we can see that our performance of our DistillNet here, we achieve substantially better performance as detection only using any of the individual modalities. And this is because we distill knowledge from multiple modalities to an unlabeled modality, audio, and we do this completely in a self-supervised manner. All right, unfortunately, I'm afraid the sound doesn't play, but here we can see basically the detections on the visual frame. Here, the network only hears the audio. That's important to note, and it will give the output on the visual field, as you can see here. All right, to wrap up this talk, we have seen methods that enable efficient performances by combining the learning of multiple complementary tasks together. And we can do this quite well using images and LiDAR scans. We also saw some work for holistic modeling of scenes, dynamic scenes, by combining 2 different tasks, that's Panoptic segmentation and multi-object tracking. We also saw 2 ways to incorporate self-supervision by exploiting the embodiment of the robot itself, as well as by exploiting supervision from complementary modalities, very different complementary modalities such as audio and vision. So with that, I would like to thank my collaborators, my students, as you can see here, because all of this work is primarily their work. So if you're interested for any of the code, then you can go to our website here and try it out yourself. So with that, thank you. And this brings us to the end of my talk.
Thank you very much for the comprehensive and nice talk. I think we can take questions from audience. So.
Hello, I would like to ask a question. Thanks for your great talk. You mentioned that you collect the data set for audio and visual data. Are there also existing data sets for that purpose, or?
No, unfortunately not. So there's actually one data set, I think, from MIT that has one microphone and a RGB camera. They just use a smartphone for this, but not at the scale, and they don't employ it on a car. So they basically, what they do is that, that was the method that we compare with, stereo SoundNet. So they basically hold a camera like a phone, right? And record a video of just walking around in the streets. And with that, they show that they are able to track objects when the camera is static. And this is because you can only do this with one microphone if the camera is static. So if you want to do this when the camera is moving around, then you need to have more than one microphone to do this pretty accurately. So the data set that we have is the only data set, as far as I know, which has multiple visual modalities and more than one direction of a microphone available.
And you do the experiments for detection task only, yeah?
Detection, and then we use tracking on top of that. But for tracking, we only employ a common filter based approach on the bounding box detections. Here, we didn't do any learning based tracking.
Okay. Thank you. It was interesting.
I have a question, actually. So at the beginning, you mentioned, so for semantic segmentation and panoptic segmentation, you have some networks that is pre-trained on other data sets. So I was wondering how to select these data sets, actually, or is there any, or does it really have an effect to select these pre-training data sets? So should it be diverge or similar? Yeah.
That's a great question. And this is also a very upcoming field with meta learning, basically. So I think more about like 3 years ago, it was primarily based on ImageNet, right? The largest data set exists was ImageNet. We all pre-train on ImageNet and then deploy it on for any other task. So luckily by now we have large data sets, annotated data sets for many specific tasks. And that's why, I don't know if you remember in the table, we had one that's pre-trained on ImageNet. That was the first one. And then the one that's trained again on Mapillary Vistas. And you could see there, the improvement that you approximately get is about 2 percentage points. And this is significant if you consider that, you know, as you go up the higher point scale, 2% is like a lot for just using a pre-training on a different data set, right? So this plays a really large role. And if we're lucky, now we have certain data sets for certain tasks that we can use. But I think what is really interesting is that we can employ meta-learning approaches now for pre-training. Like we can, how do you select the right data set for pre-training is a task itself that you can learn. So if you're interested in this, you can, there are many meta-learning approaches to do this. And another interesting thing is self-supervision, right? So you can also self-supervise your models on some pretext task. This is what we did in the audio approach. So there we got about 4% improvement using a pretext task that is basically car counting. So what we do there is that we use audio signals as input, and the output is basically to count the number of cars that the network can hear from the audio. So because we know number of cars from the detections, so we have the labels, you know, ourselves, right? So this, we don't need any annotation for this. because we can visually see the number of labels from the detections that we get. So we use this for pre-training, then our audio network. So this gives us like substantial performance in the audio domain compared to pre-training on ImageNet, because you can't really use pre-training on ImageNet for the audio because the modalities are inherently very, very different. So I think pre-training generally plays a major role, and here we can use self-supervised learning, or we can use many meta-learning methods to automatically select the best data set or the best task for pre-training.
Okay, thank you very much. We can take a few questions.
I might have one additional question regarding the proximity convolutions that you mentioned. I believe you had a size of 3 by 3 approximately. Have you noticed any sort of degradation in terms of the quality or the benefit of using these if the kernel size is getting larger?
So actually how it practically works is that you have a search area in which you employ this 3 by 3 convolution. So the search area is where you search for pixels to sample with the same range value. So the kernel size is 3 by 3, which means that you learn, for the convolution, you take 9 locations to consider for a 3 by 3 kernel. But you consider this in a search grid. So for example, for a 3 by 3, you can use a 5 by 5 search grid or a 7 by 7 search grid, or anything larger as you want. So in our work, we evaluated it and we saw that the performance is almost the same for 7 by 7 to a higher. So, 5 by 5 and higher, it's very minute improvement that you can get. But as you have a larger search area, the computation time increases. So in our work, we just use a 5 by 5 search area and we learn with a 3 by 3 kernel.
Okay. Thank you.
Yeah.
I would also have one question. This is Walter from TU Munich. So thank you for your presentation. So in the beginning, you have mentioned this efficient PS network. And on slide 12, I think you described this network and you mentioned the inference time that is about 160 milliseconds. Mm-hmm. Is there any method to improve this inference time, because it's not at real time?
So there's lots of, we haven't done any optimization. So there's a lot that you can do to make it faster. Like you can do pruning, and here we actually use the full resolution for, so if you want to benchmark your model, then you employ the full resolution, right? And then, for example, if you use a downsample image, then by half from full HD to half, then you can basically lose about 2 percentage points and half your time. So I think there's a trade-off between first the resolution of the image that you want to use to get real-time performance, and then you can do all of these things to make your network faster, right? Like you can do pruning, you can do quantization. You also have TensorRT, which is directly from NVIDIA to make your models faster for deployment. And in this work, we didn't do any of that. And I think if you employ all of pruning and TensorRT in one work, we came down to 70 using still the same resolution with a performance drop of about 2.6 percentage points. So you can further reduce this if you use a lesser resolution image than full HD, as we do here for benchmarking.
Okay, thank you.
Okay, I would like to thank you, Abhinav, Valada, for the nice presentation and informative presentation. Thank you again.